Hi everyone. So today we are going to deal with normal depth and critical depth problems. So in open channel flow, the water surface is exposed to the atmosphere, unlike pipe flow where pressure usually drives the flow. But in open channel flow, gravity is the driving force. So let's review some of the concept. So one of the important concept is Manning equation for uniform flow. So here we can see Q is equal to Km by N area times hydraulic radius, which is A by P, and and this is slope SE, is the channel bottom slope. So this Km varies with SI unit and BG system. So for SI unit, Km is 1, whereas for Km, yeah, the value of, uh, sorry, for BG system, value of Km is 1.49. So here, when we review the concept, like N indicates roughness coefficient, whereas SE or S naught represents channel slope, and there is a cross-sectional area of water surface, hydraulic radius, normal depth, critical depth, and a normal discharge and mean velocity as well. In uniform flow, water depth stays constant along the channel. This means bottom slope equals the energy grade line slope SE. The depth under this condition is called normal depth. And for critical depth, we will be using this formula uh, for rectangular channel. And some of the typical values for Mannings and are we will be using this concrete value of concrete that is 0.013, and we will be also using the earth excavation clean, which has range of 0.0222 to 0.026, whereas we will be also using this natural channel clean and straight, which has range of 0.025 to 0.035. Similarly, we will also need geometry formulas for different channel shapes. So here is some quick reference. So for rectangular type, how we gonna calculate area and weighted perimeter and hydraulic radius. Basically, if we know area and weighted perimeter, then hydraulic radius can be determined. So here in this four problems, we are just given rectangular and trapezoidal sections. So we will be using these area and weighted perimeter for these two section type. And one of the important note that I want to remind you is inclusion of M. This M, it is the side slope expressed as M is to 1, that is horizontal is to vertical. So if m is equal to 2, means for every 1 feet or 1 meter of vertical rise, the channel widens 2 feet or meter horizontally on each side. And from the graphical approach also, we can compute the normal depth. So from we'll be using this figure as well for computing the normal depth as well, since if we are given the values for discharge, we will be knowing the value of km, obviously slope and width of channel and this and as well. Then we can compute the normal depth from the graphical method as well. So I will refer some of the in solution. I may refer about this figure 6.4. You should consider looking back to this before after, and we will be also using for using this graph for computing the YC, that is critical depth for the trapezoidal channels. So as a whole, you can see here for trapezoidal channel, this graph can be used for computing the critical depth, whereas for computing the normal depth, we will be using this graph. So the first question is about finding the trapezoidal discharge channel discharge. Let us read the question first. Trapezoidal channel has bottom width that is 30 feet. Its bottom feet we have written here as 30 feet, and side slopes of 2 is to 1, horizontal is to vertical. So side slope m is equal to 2, and the channel is paved with concrete surface. I already mentioned about this concrete surface by showing in table of Manning's value, so which is equal to 0.013. It is from table 6.2, and the slope is 0.001. This S, and it carries flow depth at 6 feet. That is normal depth is 6 feet. And since all the units are in BG system, so we will be using the value of Km as 1.49. So here we just need to find the discharge value. So let us first compute the area and perimeter, weighted perimeter, then we can compute the discharge. So from table 6.1 for trapezoidal channel, the area is equal to B plus my times y. So after we compute, we will get 252 feet square, whereas for weighted perimeter, we will be using this formula to get the value for weighted perimeter, which will be equal to 56.8. I will encourage you to double check this calculation. Maybe uh, I may have some error due to calculation. So after we are done with computing area and weighted perimeter, we can compute hydraulic radius, which is A by P. That gives us 4.44 feet. And after that, we can apply Manning's equation. So it's just, we already know the formula, and we will input the value for A and RH and S. So from that, we get like discharge value is 781 cubic feet per second, which is from direct Manning equation. Similarly, like I already mentioned, we can compute this discharge from discharge or compute a normal depth from the graphical method as well. So for y-axis, it was given like a yn divided by b, because yn is our yn in normal depth is 6 feet, and b is our 30 feet, so that gives us 0.2. Since m is equal to 2, and on x-axis, like we have given n times q divided by km times slope to the power 1 by 2 times b to the power 8 by 3. So on interpreting on these things, we get like value 0.08, and when we use that value, we can get the we can solve for q. So from solving graphical, we get like 798 cubic feet per second. So that's our graphical solution. So these two answers, like from the Manning's equation and graphical solution, they differ slightly because reading values from a chart introduces small errors. So both are acceptable. On exam, the direct calculation, like from the calculation of Manning equation, is more preferable and precise. So you can follow that. So now let's jump into problem 2, which is about finding the rectangular channel normal depth. So we are given 4-meter wide rectangular channel which carries a discharge of 70 cubic meter per second, and channel has slope of 0.041 and Manning coefficient of n is equal to 0.022. So it states us to determine the normal and critical depth. So uh, basically, it asks about the computation of normal depth and critical depth. So let us jump into the finding the area and weighted perimeter. So for rectangular channel, area is equal to by, which will be equal to 4 times y, and for weighted perimeter it will be equal to b plus 2y, which will be equal to 4 plus 2y. Since y is normal depth, so we don't know that, and from many equations, since the all the units are given in SI units, so we will be using km is equal to 1. So uh, q will be equal to 1 by n times a times hydraulic radius to the power 2 by 3 times slope 1 by 2. So that gives us like this equation 1. Equation 1. So here we don't know the y. So for computation of y, we can use successive substitution, that is trial and error. So first we will guess the value of y, and if LHS will be equal to or nearby RHS, then we can use that value as normal depth. So let us use for uh, y is equal to 2 meter. So since we know this will be our LHS, and this equation will be our RHS. So when we use y is equal to 2 meter here, then it gives us equal to 8, which is slightly higher. Again, we can try using y is equal to 1.9. So that gives us LHS is equal to 7.7 and RHS is equal to 7.5, which is less. Again, let us try slightly bigger than 1.9 and lower than 2 meters. So let us try using y is equal to 1.95. So LHS is equal to 7.7, whereas RHS is equal to 7.73. So here these LHS and RHS, they are close. So we can say that value for normal depth can be it will be yn will be 1.95, and similarly from figure 6. So let's talk about graphical approach. So for rectangular channel, m will be equal to 0, and when we compute the this x-axis, it will give us 0.88, and when we interpret value in terms of y-axis, then it will be read as, this will read as 0.5. So that gives us yn equal to 2 meters. So since these are all approximate, so I suggest you to follow this successive approximation that give us value for normal depth as 1.95. So now let's go for computation of critical depth. So for finding the critical depth, it is critical. First, I think first we need to set a Freud number as 1, and we can use the formula for rectangular channel uh, as this, whereas this q is equal to q by b, and our q is equal to 70, whereas b is equal to 4 meter. That gives us 17.5 meter square per second, and we know gravitational acceleration due to gravitational, so which is 9.81 meter per second. So when we put here, so our yc is equal to 3.15 meter. So hence our normal depth is equal to 1.95 or 2 meter, and critical depth is equal to 3.15 meter. So I suggest you to again double check my calculation, uh, but approach is fine. So it is also same like question number two, but the channel is different. Like it is a trapezoidal channel and it has unit of BG system that is in feet. So it has the width of channel is 15 feet and side slope that is equal to 2. That is, we can use m as 2. And we are also given discharge of 1000 CFS, which is Q. And it has the natural channel that has 0.01 feet by feet bottom slope. That is uh, n, sorry. So for natural channel, that is clean or straight, n is equal to zero point 0.0 feet by feet, which is from table 6.2, whereas bottom slope is equal to 0.01 feet by feet. And since it is busy system, we need to take care about units. So km will be equal to 1.49. So since we don't know the normal depth here as well, so like previous question, we will be using the successive iteration, like testing the value of different yn and computing the LHS versus RHS and getting into the equal or approximate value for yn. So similarly, I calculate area and perimeter. So after that, we know the Manning's equation. So I use that here. After that, for easier computation, I rearranged the term here to make area by weighted perimeter uh, equal to 201.3. So basically, it will help me to compute A by P easily with using this formula. So we just need to input the value of y. So in next step, I will use the value of y as 1. So that gives us area as 17 and weighted perimeter as 19.5. And when we compute a by p, that gives us 15.6, which is not equal to 201. So I choose the smallest one. So next time I can choose like bigger one. So let me use y is equal to 3 feet, and that give us 107.25, which is also not uh, close to 201. So let me use like a bigger number, uh, 3 times previous value, that is 9. So that give us like 911.7, which is way far from the 201. So let me come back into half of that, and that give us like when I use value of y as 4.5, and area will be equal to 108, p is equal to 35, and when we use that equation 1, it give us 228.9. It is slightly closer to 201, but let me be precise. Let me go down and use uh, value of a normal depth as 4.2. That give us closely like 209.3, and we can say that normal depth as 4.2 feet. And similarly, we can also use graphical method for computing the uh, normal depth here. I have not done here, but it can be done. And now for critical depth, like I already talked about, we can use graphical method here, that is stated in figure 6.9 in the review section. So I have used that, and y-axis is equal to mc m times critical depth divided by b. We don't know the value of this YC. So we will be interpreting the value obtained from x-axis to the y-axis, and on interpretation, we will get like a value of approximately 0.8, and that give us value of yc, that is critical depth, as 6 feet. So this is from this x-axis. It is given from that figure, so I will not describe more about this. So it's just putting the value on the equation. So I have not done anything apart from that. So one thing I have done is I uh, interpret this. So now let us go to problem 4. Uh, it is related to channel with change, that is finding new normal depth. So we are given the uh, channel of width for first part as 12 feet, and discharge is given as 1520 cfs, and normal depth is given as 15 feet before change. And after channel expands, that is it became 20 feet width. So we need to find the new normal depth, that is y2. And here the question asks us to assume slope and channel roughness as constant for the both channel. So now let us use the Manning's equation. So since it is also in BG system, so we will be using this 1.49 value for Km. So Q will be equal to 1.49 by N times area times hydraulic radius to the power 2 by 3 times slope 1 by 2. So that give us, let us rearrange this slope and n because they are constant. So I arrange this like this, and for since this uh, hydraulic radius is area by p, so I rearrange that and it became like this. So it will be easier for computation in later. So since it is rectangular channel, so area is equal to by, p is equal to b plus 2y. Now let us set up the ratio. Since 1.49 times slope to the power 1 by 2 divided by n is same for both the channel, we can eliminate them. We can eliminate whole this part. And since we already know this q, we will have just this a by p term. So for first part it will be like this, and for second part it will be like this, and that is a1 divided by p1, a2 divided by p2. And when we use the uh, width of channel and normal depth by computing area and p for first part and second part, they look like this. This b1 times y1 to the power 5 by 3 divided by b1 plus 2y1 to the power 2 by 3. Similarly, this b2 times y2. And when we rearrange, let us make rearranging this term into uh, similar kind. That is, it has power 5 by 3 in LHS, and in RHS we have power 2 by 3, so it will be easier to do the computation later. So let us input the values that we have here, so that only there will be only remaining part is y2, that is normal depth after change, and here also normal depth as after change. So after rearranging these things, we will have this final equation as 1. So that will be equal to LHS is equal to 3.24, is equal to y2 to the power 5 by 3 divided by 20 plus 2 y2 bracket 2 by 3 power. So we have this equation. So now let us use the same technique, that is hit and trial or trial and error approach. So let us use value of y2 as 10 feet first. So our LHS is 3.2. Let us compute just for RHS. So that give us 3.96 feet, and we our LHS is 3.24. So it is slightly higher. So let us do Y2 as 9 feet, and that give us 3.44. It is also slightly higher than 3.24. Again, let us choose 8.5. So that give us 3.18. It is lower than 8.4. Now let us again be precise, like use Y2 as 8.7, and that give us 3.29. So the value between 8.5 and 8.7 uh, will be the new normal depth. So that is maybe like it is not precise, but approximately 8.6 feet. So here in this question, one of the important thing you need to consider is like maybe you didn't see the value for S and N and are considered as unknown. So uh, the question already mentioned about they are constant, so you don't need to worry about that. You can eliminate them through the ratios. So this wraps up our critical depth and normal depth recitation class. The big idea is Manning equation, which is used everywhere in these four problems.